Today, we're diving into advanced machine learning techniques, exploring powerful methods beyond the basics. We'll go beyond the fundamentals to achieve smarter predictions and more robust models in our data analysis. Let's begin by understanding decision trees and then move on to the powerful random forests. These techniques combine simple decision-making rules into highly powerful, accurate prediction systems. First, let's explore decision trees, a fundamental concept in machine learning for classification and regression. A decision tree is a tree-like model that makes decisions by splitting data based on various features. It recursively splits the dataset into smaller subsets, making decisions at each node based on feature values. Decision trees are very intuitive and easy to understand, often visualized just like a simple flowchart. However, a single decision tree can be prone to overfitting, especially with very complex datasets. Now, let's look at random forests, an advanced technique designed to overcome the limitations of single trees. A random forest is an ensemble method, meaning it combines predictions from many individual decision trees. Each tree in the forest is built using random subsets of the data and a random selection of features. This ensemble approach significantly reduces overfitting and greatly improves the overall predictive accuracy. While powerful, random forests are generally less interpretable than a single, straightforward decision tree. Let's walk through the step-by-step process of how we actually build a decision tree model. Every decision tree begins with a start node, representing our entire dataset before any splits. At each step, the data is split based on a chosen feature, aiming for the purest possible subsets. This recursive splitting continues, building the tree layer by layer until stopping criteria are met. After construction, we often prune the tree to remove unnecessary branches, preventing overfitting and improving generalization. Finally, the pruned tree is ready, and a prediction is made by traversing the tree to a leaf node. Now, let's explore the robust process behind a random forest, combining many trees for accuracy. This powerful method combines the predictions from multiple decision trees to yield a very strong result. The process starts with bootstrap aggregating, where multiple subsets of the original data are randomly sampled with replacement. For each split in every tree, only a random subset of features is considered, adding more diversity. Using these random subsets of data and features, many independent decision trees are then trained. Once all trees are trained, their individual predictions are aggregated, typically by averaging or voting. This aggregation leads to a final, robust prediction that is more accurate and stable than any single tree. Let's now explore the key differences between various machine learning models we've discussed so far, which is crucial. Understanding these distinctions will help you choose the most appropriate model for your specific task and dataset. First, let's look at decision trees, a foundational model in machine learning for classification and regression. A decision tree is characterized by being a single, standalone tree model, making it quite straightforward. One of its major strengths is that it is incredibly easy to interpret and visualize, offering clear decision paths. However, a significant drawback is that single decision trees are quite prone to overfitting, especially with complex data. They also generally have a lower computational cost, making them relatively quick to train and execute. Now, let's consider random forests, which build upon the concept of individual decision trees for better performance. Unlike a single tree, a random forest is an ensemble of many decision trees, working together collaboratively. Due to this complexity, random forests are generally less interpretable compared to a single decision tree model. A key advantage of using an ensemble is a significantly reduced risk of overfitting, leading to more robust models. Naturally, combining many trees means random forests come with a higher computational cost during training. Let's dive into the core ideas behind gradient boosting, a powerful technique for building predictive models. The main concept here is building strong, accurate models by sequentially combining many simpler, weaker learners. A weak learner is typically a simple model, like a shallow decision tree, that performs slightly better than random chance. The learning rate controls how much each new weak learner contributes to the overall model, preventing overcorrection. The loss function quantifies the error of our model's predictions, guiding the boosting process to minimize this error. Finally, sequential training means we train weak learners one after another, each correcting the errors of the previous ones. Now, let's compare two highly optimized gradient boosting frameworks, XGBoost and LightGBM, both very popular. These algorithms offer optimized boosting, but they cater to different needs depending on your data and resources. First, let's examine XGBoost, known for its powerful performance and comprehensive features in machine learning. XGBoost grows its trees in a depth-wise manner, meaning it expands levels evenly before moving to the next. It's particularly excellent for small to medium-sized datasets, where it often delivers top-tier performance. However, XGBoost tends to have higher memory usage, which can be a consideration for very large datasets. It also offers many hyperparameters to tune, giving you extensive control over the model's behavior. Next, we have LightGBM, an alternative boosting framework designed for speed and efficiency, especially with big data. LightGBM employs a leaf-wise tree growth strategy, focusing on growing the leaves that reduce the loss the most. This approach makes LightGBM significantly faster for large datasets, a major advantage in big data scenarios. It also boasts lower memory usage compared to XGBoost, making it more efficient for memory-constrained environments. A convenient feature is that LightGBM natively handles categorical features, simplifying data processing steps. Let's compare two fundamental clustering algorithms, K-means and DBSCAN, which approach data grouping differently. These are two distinct approaches to grouping your data, each with its own strengths and ideal use cases. First, let's look at K-means, a widely used and intuitive algorithm for partitioning data into clusters. A key requirement for K-means is that you must specify the number of clusters, K, upfront. K-means inherently assumes that clusters are spherical or blob-like in shape, which might not always be true. It's generally quite efficient for large datasets, making it a popular choice for scalability. However, K-means is quite sensitive to outliers, as they can significantly pull cluster centroids away from true centers. Now, let's explore DBSCAN, a density-based spatial clustering of applications with noise, offering a different perspective. A major advantage of DBSCAN is that it does not require a predefined cluster count, finding them automatically. It excels at finding arbitrarily shaped clusters, which is great for non-spherical data distributions. DBSCAN is also robust, as it can effectively handle noise and outliers, classifying them as non-cluster points. However, DBSCAN can be sensitive to its density parameters, epsilon and min samples, requiring careful tuning. Let's now explore the main types of recommender systems that you encounter every day online. We'll delve into how these intelligent systems actually suggest things you might genuinely enjoy. First up, we have collaborative filtering, a very popular and widely used recommendation technique. This system recommends items based on the past behaviors of similar users or similar items. Next, let's look at content-based filtering, another fundamental approach to recommendations. Here, recommendations are made using item attributes and a detailed understanding of your user profile. Finally, we often see hybrid systems, which combine the strengths of different approaches. These systems cleverly combine various recommendation techniques to provide even better, more accurate suggestions. Let's now recap the key concepts we've covered in our discussion on advanced machine learning techniques. Here are the essential takeaways and important points that you should remember from this lecture. Remember, decision trees are easy to understand, but they can easily overfit the training data. Random forests improve upon this by using many trees, reducing overfitting and boosting overall accuracy. Gradient boosting methods, such as XGBoost and LightGBM, refine predictions by iteratively correcting errors for high performance. K-means clustering groups data based on distance, but it always requires you to specify the number of clusters. DBSCAN, on the other hand, finds density-based clusters and effectively handles noise without needing a cluster count. Finally, Recommender systems personalize suggestions using collaborative, content-based, or hybrid filtering techniques.